So once we look at, okay, how to draw a good graph. These were, all the different things we discussed. So just a summary of what it takes to draw a graph. We got into polynomial inequality. So we looked at one example where we were using the graph to try and come up with the solution. So I actually wanted to look at one more example based on the graphing method before we did the test point method. So let's take a look at how it's in the Okay, so it's kind of very similar to the example we had from the textbook. So you can see it's asking us to state the solution of the inequality by reading the graph. So our inequality is x to the fourth power plus 900 greater than or equal to 61 x squared. Now, obviously, before you start solving for this, it's a good idea to put this in the standard form. So move all the terms on one side, get 0 on the other side. So this guy here. X to the fourth. We'll take that positive 61 x squared and move it to the left-hand side. So that will end up becoming negative 61 x squared. And then we have the plus 900. And since we move the 61 x squared, you will end up with greater than or equal to 0 on the right-hand side. So that's basically telling us if we think of this as being, y equals this expression, x to the fourth minus 61 x squared plus 900, we're basically saying where is your y value greater than or equal to 0. Now, last time the example we had seen was just greater than, but this one is doing both greater than and equal to. So what will that look like with our graph? So like I said, we're interested in where the y value is going to be a positive number and where the y value is going to be greater than 0. So any place where the y value is going to be a negative number, we leave that out, right? So anything that falls below the x-axis, that's where we know our y value is going to be negative. So what interval do you think will satisfy this inequality where the y or our inequality is greater than or equal to 0? What do you think that interval notation will be? So what is it going to be? Go ahead.
We're going to see negative infinity, comma 6 or negative 6.
Okay.
And then bracket u bracket 5 to 5 again, or negative 5 to 5.
Negative
Another bracket u, and then bracket 6 to positive.
So let's take a look at these intervals that, as I just mentioned to us. So you're going from negative infinity, which of course is somewhere over here, coming all the way to negative 6. So that's going to include this part of our graph, right? So yeah, all the y values here are going to be positive. Right at negative 6, we have a y-intercept, right? So the right at that place is where your y value is equal to 0. Now, between negative 6 and negative 5, our curve is falling below the x-axis, right? So that's where we know the y values are going to be negative. So we leave that part out and we pick right back up at negative 5, which again is a x-intercept, so your y value is greater than 0. And then so we keep going, all of these y values here are greater than 0, that looks good, and then you again stop at positive 5. Again, that is where the y value is equal to 0. We pick right back up at positive 6. And everything to the right is again going to have y values greater then 0. And since this guy is specifically asking us greater than equal to, we do include the endpoints, right? And that's why we have those brackets are -6, -5, +5, and +6. Alrighty, wonderful, very nice. So yeah, this is how we use the graph to help us solve our inequality. So let's save this and then type our answer. So we are going from -infinity to -6 with a bracket. I'll come back with my union symbols. Then we are going from -5 to +5, bracket again. And then bracket 6 to +infinity. Now let's go ahead and put those union symbols. Everybody okay on this? Did anyone have a question? Yeah.
If it was just greater than, they would just be parentheses and not brackets then.
Yeah, same exact interval, just with parentheses. Yeah, very good. Alrighty, anybody else? Question? Okay, all right, let's see what we can. That's one more. Ah. Mm, mm, mm. Do this one. All right, we've got x to the 4th minus 4x squared less than equal to 0. And they want us to solve this using the test point method. So test point method means we need to find out where our x-intercepts or our zeros solutions are going to be. So how do we solve this polynomial? Find its zeros. X to the 4th minus 4x squared, and we'll of course solve it as an equation for now equal to 0. Because we're finding our x-intercept. So what do you do to solve this guy? What method can we use?
What's called is the -45 to a.
Oh, you're talking about the quadratic formula? Or just the negative b over 2a part?
Yeah.
You wouldn't use that. Because remember, that is either if you're finding the vertex of a parabola or if you're finding the axis of symmetry. And since we're doing neither, that wouldn't work here.
So it's already solved.
Factor.
Factor, right? Because in this case, we can see there are two terms and we have something common between the two terms, which is what? What's wrong with you today?
I wonder.
Yeah, because these are not your normal answers. What's common?
X squared.
X squared, yeah. So we will start by factoring out x squared. So from x to the 4th, if we subtract 2, of course, you're left with 2. So that means 2 of the x's are left behind. And of course, we take the x squared out, so you're left with -4. Take each one of those factors, set it equal to 0. And then remember, using multiplicity, we can see how many solutions we have and what those solutions will be. So of course, x squared equal to 0, you'll take a square root on both sides. Normally we get a positive or negative, but since our answer is 0, you'll just end up getting x equals 0. However, that does tell us, since this came from the factor of x squared, this has a multiplicity. X squared minus 4, what will that simplify? Yeah, you get both positive and negative too. So we start by moving the 4 to the other side. You get x squared equals 4. Same thing, you end up taking a square root, which gives us a positive and a negative root. Square and square root cancel out, giving us plus or minus 2. Now these guys will of course have multiplicity 1, because the positive 2 occurs once, the negative 2 occurs twice. Okay, so draw a number line, and this is basically representing the x-axis. We'll put our x-intercepts on there, so we have 0, +2, -2. So remember, with the test point method, from each interval, we pick a test point, right? So of course, we are heading in towards negative and positive infinity here, and then let's pick a test point from each interval. So let's start at the leftmost interval. What test point can we use there?
-3.
Yeah, -3 works between -2 and 0. -1 between 0 and 2. And between 2 and infinity. All right, so we've got our test points. Now, all we need to do is check them in our original polynomial, right? And see if we get a positive or a negative sign when we test. So let's go ahead and check our answers. We'll of course start with x equals -3 as our first test point. So when we put that into our polynomial, we'll have -3 to the 4th power minus 4 times -3 squared, which will end up giving us 4.
Oh, sorry. Um,
Because you're missing something. -3 to the 4th power will be a positive number, right? It will become a positive 81. 3 squared or -3 squared will also become positive, so that'll be positive 9. 9 times 4 will definitely give us the -36, but what's the final? Yeah, and this is a positive number, right? So that tells you our sign on that interval is going to be positive, which means all the y values in that interval are going to be a positive. Alrighty, let's check our second test point, which is x equals -1. So same thing, -1 to the 4th power minus 4 times -1 squared, and what will this value be? Final answer 1 or just the first?
First,
Okay. Minus 4 again, because 1 squared will be 1 again, so this is giving us -3, right? That means all the signs in the second interval are going to be negative, so all the y values in the second interval are going to be below the x-axis, right? Negative values. What about with x equals +1? What will this give us? What kind of sign will we see on that? Yeah, you will actually end up with the same thing because 1 to the 4th power is 1, 1 squared is 1, so that's 1 minus 4. It still gives us -3, so this guy will also have negative y values. And then for our last interval, I guess I'm going to do that. X is +3. So we will again have 3 to the 4th power minus 4 times 3 squared. What will that guy give us? Yeah, we will actually see symmetry here. So same thing, 81 minus 36, which will give us a positive. All right, so now we know where our y values are positive. Again, remember your y values are 0 right at the intercepts, right? They are asking us for where is the inequality going to be less than 0. So technically they want to know where the y value is less than 0. So what interval can we use to satisfy this inequality? So we need the interval, not the test. So between like what numbers will this be satisfied? Yeah, you cannot just go all the way from -2 to 2 because we're not including 0, right? So we will actually need to do -2 to 0 and then 0 to 2. If they had given us a little equal to, then we could have gone directly from -2 to +2, but since this is a strictly less than, we have to take that into account. So this will be, can I really run no space? Guess I'm gonna go up here. So your solution set will be, and again, we're not including the endpoints here, guys. So you're going parentheses, -2 to 0, close parentheses. And then again, union symbol. It right back up on the other side of 0 and then to +2. So basically, I guess we're looking at this endpoint here, not including the endpoints, and then this. Because that's where our y values are negative. So test point method and graphing method. Any questions on this one here, guys? Anybody on Zoom question on this? All right, I just want to very quickly show you what the graph for this now will look like, and then we'll move on to. So we have x 4 power minus 4x. It's kind of hard to see with all the writing, but I'll erase the writing. I just want to point out that our intercepts do in fact match where we had them. So you will see -2, 0 was one of our intercepts. Of course, 0, 0 was also one of the intercepts, and then we had +2, 0. So you can see those are where all the y values are going to be equal to 0. Anything above the x-axis, y values are positive. Anything below the y-axis, the y values are negative. So you can see it's of course going to be this interval here that we did between -2 and 0, where we see y values is negative, right? And then you pick up on the other side of 0, where again your y values are. Again, this was a simple enough function that we were able to use the graphing on this one, but again, you guys should be comfortable going back and forth between the graphing method and the test. Alrighty, wonderful. So that will be section 3.4. Let's see. So 3.5 actually gets into rational functions. So we've been talking about polynomials so far, but when we talk about rational functions, we're actually talking about having polynomials in both the numerator and the denominator of your function. So remember, rational number is a number that's defined as a number that can be written in the form a over b. So that's what a rational function is. A rational function should also be able to be written in the form a over b. So you can see some examples over here. We're talking about y equals 1 over x, or something like f of x equals 2x minus 3 divided by x plus 4. So since we do have the x value of our function in the denominator, we will need to be careful about numbers that make our denominator 0, because again, we need to avoid those, right? Again, division by 0 is undefined. That is going to work out with rational functions also. So you do not want to have any number in your domain which will make the denominator a 0. So we will need to discard those. So remember, again, both numerator and denominator can be polynomials, provided that the denominator function is not a 0 polynomial, which means it won't be equal to 0. So your textbook says, to simplify the discussion, we will assume that the rational function given to us is in the lowest terms, but every now and then you will see there may come up an example where it's not in the lowest term, and we'll need to put it in the lowest term. And that can actually affect what the function will look like and what its domain and range could be. So we'll kind of look at that, just a couple examples, but we'll run into those. But for the most part, we're going to assume the functions are in lowest forms. So they're saying the domain of a polynomial function is the set of real numbers. And we did see that in the previous sections, but most of them had the set of real numbers as the domain. However, as I just mentioned, since we are dealing with polynomials in the denominator of rational functions, you are going to have restrictions on the domain. So any number that would make the denominator 0 has to be discarded. So you can think about the basic function y equals 1 over x. Well, we know if I have 1 over x and x is equal to 0, I'd end up with 1 over 0, which would make it an undefined So we say x cannot be equal to 0. So for this function, we would say it's the set of all real numbers except 0. And of course, in interval notation, that will look like this. All real numbers except 0. So let's talk about just for different functions, what the domain would end up with. All right, so let's take a look at this right here. So our function is f of x equals 2x squared minus 3 divided by x squared minus 4x. So we're interested in finding out what makes the denominator 0. So that's exactly what we're going to do. We're just going to look at the denominator polynomial, x cubed minus 4x, set that equal to 0, and find out what value of x is going to make the denominator 0. How would we simplify this guy? So you're basically solving a polynomial, trying to find its roots. What would we do? Yeah, same thing we did before, factor. So x would be the common factor. So out of 3, we're taking 1 out. You're left with 2. So again, you'll end up with x squared minus 4. Set each one of the factors equal to 0. Solve. And since we already did this math, literally a couple minutes ago, I'm going to skip the answer. So that will simplify into x equals plus or minus 2, right? Take the 4 to the other side, take the square root, and you get x equals plus or minus 2. So there's actually 3 numbers that are making our denominator 0. And you can do a quick check to verify. If I did 0 to the 3rd power minus 4 times 0, of course, 0 minus 0 is going to be 0. So we know this guy works out. With positive 2, that would be 8 minus 8. So again, you're getting a 0. With negative 2, that would be negative 8, positive 8, which would also end up becoming 0, right? So you can see all 3 of those numbers are making our denominator 0. So all 3 of them need to be kicked out of the domain basically. So we are saying we cannot use 0, we cannot use negative 2, and we cannot use positive 2, which means every other number is going to be fine as long as it's not these 3 numbers. So this is what your interval would look like. So the domain for this guy is going to have what, 4 parts to it? Negative infinity to negative 2, not including the number. Then we go from negative 2 to 0, again, not including the endpoints, going from 0 to 2, and then from 2. And I like drawing the number line because then it gives me a visual reference, right? I can see, okay, these are the 3 numbers that didn't work. My domain is broken up into 4 intervals. So when I'm typing out my notation, I know what it will look like. Should I just go ahead and type our numbers on and I'll do that? Union symbol. So let's see, we're going from negative infinity to negative 2, and this is all the parentheses. Then negative 2 to 0, 0 to positive 2, and then from positive 2 to positive. Alrighty, and now I can type in our union symbols. So let's check that. There we go. That looks good. Question on this one, guys. So that's going to be a process for finding any domain for these rational functions is just take the polynomial on the denominator, set it equal to 0, and then see what answers you come up with for your x value. And those numbers that you're finding are the ones you're not including, right? Those are the ones that get discarded. On Zoom, did anybody have a question on this? No, are we doing okay? Not seeing anything come up on chat either. Okay. All right, so now that we're talking about rational functions, there's a new concept I'm going to introduce, or maybe you've heard of it before. It's what we call as asymptotes. What the asymptotes basically tell us is that the value of your function is getting closer to a number, but it's actually never going to include that number or be equal to that number. It just keeps getting closer and closer to it. And as it gets closer to it, your graph will actually start going towards positive or negative infinity. So you can have horizontal asymptote, which means it's going to be an imaginary horizontal line that your graph is getting really close to, but it's not going to touch that line and it's not going to cross. Well, having said that, there are actually some functions which can actually cross a horizontal asymptote. But again, it's a very different type of function that does that, and we'll talk about it. So you can have a horizontal asymptote. Now you can also have a vertical asymptote. So the same thing happens. Your function is getting really, really, really close to this vertical line. But for vertical asymptote, it's definitely not going to touch and it's definitely not going to cross. And here's the best part. You already know how to calculate a vertical asymptote because it's going to be at those same points where it's not included in under. So like we did -2, 0, and +2 on that last function, that's where your vertical asymptotes will be. So those graphs will get really, really close to those, imaginary vertical asymptote lines, but it's not going to touch these lines. It's not going to cross them. And you can also have an oblique asymptote. So vertical, horizontal, and oblique are the three types of asymptotes we're going to talk about. So you can see with this little illustration here, we're talking about the function f of x equals 1 over x. This guy has both horizontal and vertical asymptote. So we know our x value cannot be equal to 0 because that's what makes our denominator 0. So your vertical asymptote is actually at x equals 0, which is this imaginary line over here. So which is basically also our y-axis. So what's happening is you will see our graph is getting really, really close to it. So, the value of the y, x is getting really, really close to 0 here, but the y value is actually headed upwards towards infinity. So you can see as x is getting closer to 0, your y is actually heading towards infinity. Same thing is happening on the other side. So as we come closer to 0 from the left-hand side, same thing happens. My x is getting really, really close to 0, but now my y is heading towards negative infinity. And we can test this with numbers. You don't have to just look at the graph for that. So look at this little table over here. So we're coming, of course, we're not going to be anything equal to 0 because that's where it's undefined. So you can see there's an empty box there. But think about, I'm coming from the right-hand side and I'm getting closer to 0. So when my x value is 0.1, my y value is 10, I get even more closer to 0. So I'm at 0.01, but you can see this guy has jumped to 100 now. As I get even more closer to 0, this becomes 1,000. So this is what we're saying. As x is getting closer to 0 coming from the right-hand side, so from the positive side, your y value is headed to positive. If I come from the left-hand side, which is this one here, so I'm coming in from the left-hand side on 0, I'm at negative 0.1. You can see my y value is at negative 10. Now my x is at another step closer, right? Negative 0.01. My y value jumped to negative 100. And again, as I get closer, this number gets really large. So as you are coming to the x value of 0 from the left-hand side, the negative side, the y value is going down to negative. And that's because of that vertical asymptote there, because again, my graph is getting closer to that line, but I'm never going to touch it or cross it. So, your graph starts diverting. So it's going to positive infinity on the top and it's going to negative infinity on the bottom. So that's your horizontal asymptote. Now, as I said, this function y equals 1 over x also has a vertical asymptote, horizontal asymptote. So same thing is happening over here horizontally. On the x-axis is where the horizontal asymptote is. That's the line y equals 0. So what's happening over here is, again, as your y value gets closer to 0, your x starts going to positive or negative infinity depending on what side you are at. So again, I can show you that with a table. So look at this one. As your x value gets larger and larger, you will see your y value actually starts getting smaller, right? So at -10, we were at -0.1. When we increase the x value to a -100, my y value became even smaller. Same thing's happening on the positive side. As the x value gets really large, your y value is getting really small. So it's as x goes to negative infinity, your y is getting closer to 0, and this is on the negative side. As your x value is getting closer to positive infinity, your y is getting closer to 0 from the positive side. So like I said, to find the vertical asymptote, it's the same place where your domain does not include the numbers for the denominator, but horizontal asymptote is going to be a little bit of a different calculation. Okay, so I think I already talked about that. Okay. So they are saying for any rational function that is expressed in lowest terms, the horizontal asymptote is determined by the value approached by the rational expression. So is your expression approaching positive infinity or negative infinity for the x value? Based on that, we can come up with where the horizontal asymptote is going to be. A vertical asymptote occurs for every number that causes the denominator of the function to have a 0 value. So that's where all your vertical asymptotes are going to be. Not every rational function has a vertical and a horizontal asymptote. So it's not like a default thing that they're all going to have. It just depends on how the function is defined. All right, guys, let's talk about how to find a horizontal asymptote. So if you have a function that has this format, where you have a constant number on the top and the x is on the bottom. So you'll see there's no x on the numerator. All the x's are on the denominators. You have 500 over x, 3 over x squared, 5 over x cubed, or 2 divided by x minus 5. If that is your format, guys, for the function, your horizontal asymptote is always going to be at 0. Because the value of your function is approximately equal to 0 as your x gets really, really large. And we can actually test this theory. Let's use Desmos to help us out. And I'm just going to use the 500 divided by x function. Let's do our basic scientific calculators. Okay, I'm doing the 500 divided by x function. So just start with 500 divided by 500. Obviously, it's going to be. But what if we did 500 divided by 5,000? You can see that number became smaller, right? We ended up with 0.1. What if we did 500 divided by 50,000? Now it's become 0.0. Now keep adding zeros and you see how much closer we're getting to 0 for the value of the function. So as I keep adding zeros, now it's turning to scientific notation, but basically we're now saying it's 0.0000001, and you have -5 zeros from it. So this is what happens as you get the denominator really, really large, and I can keep going, and you can see that exponent is just going to keep getting larger and larger because it's telling me that's how many zeros is between the decimal and the number 1. So if I have -23, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 23 of those before it gets to it. So think about that. So any expression, any rational function that is going to be a constant number on the top and x on the bottom, they're all going to have a value of being approximately equal to 0 when your x value is getting really, really large. So all of these types of functions are going to have their horizontal asymptote at y equals 0. Okay, because it's a horizontal line, it's going to be a y equals function. Now, what if you have an expression that looks like this, where you have the same exponent on the x on the numerator and the same exponent for the x on the denominator, which means they have the same degree, right? They're both x to the first power and x to the first power. So the process for solving this is you take each one of your terms. So I've got x and -2. I've got 2x and +3. I'm taking each term and dividing it by the highest power of x, which in this case, our highest power of x just happens to be x to the first power. So you can see every term is being divided by x, and then you simplify this. So x divided by x will become 1. So this expression here becomes a 1. 2 over x, we know as x gets really large, would start getting closer to 0. 2x divided by x, the x's cancel out, leaving us with 2. And then 3 divided by x, again, as my x starts going towards infinity, the value of 3 divided by x will start getting closer to 0. So technically, you will end up with 1 minus 0 over 2 plus 0, when I simplify this expression here. And that gives you the factor of 1/2. And that's actually where the horizontal asymptote is going to be. It's going to be at the line 1/2. So honestly, if your rational function has the same degree on the numerator and denominator, your horizontal asymptote is going to be the ratio of your leading coefficient. So this is 1 over here, and that's 2, and you can see that's the 1/2 we ended up with. So it's actually the leading coefficient of your x term that ends up becoming your horizontal asymptote, or the value of your expression as x gets rid. So that's for the same degree. Now, what if you had a larger degree on the numerator and a smaller degree on the denominator? That's actually when we run into oblique asymptotes. Okay, so before we get into oblique asymptotes, let's look at a couple examples on how to find vertical and horizontal. So let's look at this guy here. They're asking us to determine all the equations for all of the asymptotes. Now, I do want to tell you, you can only have horizontal or oblique. You cannot have both. But you can have vertical and horizontal. You can have vertical and oblique together. But between oblique and horizontal, you can have one or the other. Okay, so you won't have like all 3 of them for one given point. So to find the vertical asymptote, we will do the denominator and set it equal to 0. So take our denominator, which in this case is x squared plus 3x minus 4, set it equal to 0. And then let's find out what those vertical asymptotes are going to be. So how do we solve this guy? X squared plus 3x minus 4. Now that's a quadratic equation, right? So what can we do to solve it? Can we factor it? Yeah, what can we factor it with?
That plus 2x.
Yeah, very good. Yeah, that'll work. So we can factor this guy into x plus 4 and x minus 1. Because remember, 4 only has 2 options. You either do 4 times 1 or 2 times 2. So the combination that will work is a positive 4 and negative 1, which gives us a positive 3 when we add and negative 4 when we multiply. So that will end up giving us x equals negative 4 for the first one, x equals positive 1 for the second one. So that's where our vertical asymptotes are. And then remember, that's also the numbers we wouldn't be including in our domain. So x equals negative 4, x equals positive 1. So we of course have x equals negative 4 here, x equals positive 1 here. Okay, so choose the equations below that are vertical asymptotes. All right, we got both of them. Let's save that. Check that. Okay, and then you will see the second question pops up where we need to find the horizontal asymptote. So before we move on to that, everybody okay with the vertical calculation? Yeah? Zoom people, any questions on the vertical? No? All right, let's talk about the horizontal. So horizontal, look at the expression here. You have 2 on the top and x squared plus 3x minus 4 on the bottom, right? So we have just a constant term on the top and all my x's are on the bottom. So remember, this is where your horizontal asymptote, you don't really even have to do a calculation, is always going to be at 0. When the number on the top is a constant term with no x and all the x's are in the denominator, your horizontal asymptote is going to be at y. And again, guys, these would be things I would put on my note card for the exam. So y equals 0, let's check that. And that's it. We're good to go. Everybody okay? Yeah? All right, let's see if we have another example. There we go. All right, let's check it again. So again, we're starting out with vertical asymptote here. Let's see, we have x minus 3 as our denominator. So what's our vertical asymptote? Yeah, x equals positive. Now this one, they're actually having you type the answer and you're not choosing. So remember, you do have to type an equation there, guys. Just don't put the number 3 by itself. Put the entire equation. So x. That's it. Sorry, I put a backslash. There we go. All right, x equals 3. Now for the horizontal. So this one you will see you have 4x plus 3 over x minus 3. So both my numerator and denominator have the same degree for the x value. They're both x to the 1 and x to the 1. So remember, that tells us you're basically looking at the coefficient of the x values to get your horizontal asymptote. So that's actually going to be these two numbers here. So your horizontal asymptote is going to be the line 5, y equals 4 divided by 1, which is basically y equals 4. If we did it the other way that your textbook was talking about, we would take each one of our terms and divide it by the highest degree of x, which in this case happens to be x to the first power. So we would divide each one of these by x. So these guys would cancel out, leaving us with 4 on the top. And then, of course, we would have positive 3 over x. On the denominator, the x and x would cancel out, leaving us with 1. And then you would have minus 3 over x. So as x starts going to infinity, this guy would start going to 0. So you would then end up with 4 plus 0 on the top, 1 minus 0 on the bottom, which would still come out to be 4 over 1. The same conclusion, right? We would still end up with horizontal asymptote at y. So that's the mathematical way of doing, but the shortcut is if it's the same degree, look at the coefficients of the x values, and that's going to be your horizontal asymptote. All right, and again, you're typing this as an equation. So this guy will be y equals 4. All right, let's check that. See. And as I said, if you have the horizontal, you are not going to have the oblique, so you don't really even have to check for it. If the horizontal had come out to be as you don't have a horizontal asymptote, then you would have checked. So, this, and let's check that and give it to. Questions on this example? Daniela, Danny, Jessica on Zoom, how about you guys here? No? Okay. All right, let's talk about oblique asymptotes next. So remember, for the oblique asymptote, the degree of your numerator is going to be higher than the degree of the denominator, which means you should see a larger exponent in your numerator. So oblique asymptotes, also known as slant asymptotes, are not vertical, they're not horizontal. Obviously, they're going to be at a slant, right? Positive or negative. Oblique asymptotes can be determined by using long division or synthetic division. If you can use synthetic division, that's probably what you want to use, but there is one example that does better with long division instead of synthetic. Okay, so let's do synthetic division for this guy. Okay, so remember, for the synthetic division, you do need to figure out what you are going to be dividing by. So if it's given to you as x plus 1, set that equal to 0, which will give you x equals negative. So you're actually dividing by negative. Yeah? And then, of course, you've got x squared term, so that has a coefficient of -1. You have an x term, which has a coefficient of 2. What are we missing there? We've got x squared, we've got x, the constant. So you do need to actually make a space for it and put a 0 for the missing constant. Okay. And then again, remember, guys, synthetic division, you bring the first term down as it is. So that will give us -1 comes down, negative times negative will be positive, 1 times 1 is 1, 2 plus 1 is 3, 3 times -1 is -3, which of course then adds up to -3 as well. So remember, this is your remainder. This is your. I know I'm kind of in between writing again, but I want you to look at that paragraph above the green box. So they're saying if the degree of P of X, which is the numerator, is 1 degree greater than the degree of your denominator, and of course, the degree of the denominator has to be at least 1, then they are saying your rational function will end up with an oblique asymptote, which is our example here. So they're saying use division to write the function as quotient plus remainder over divisor. But remember, that only gives you a rewrite of the original function. To write out your oblique asymptote, you're actually taking the quotient and setting it equal to y. So there's 2 different things you will see in this oblique asymptote thing. So again, the oblique asymptote is just the quotient set equal to y, but if they ask you to rewrite the function, so like instead of rewriting the function as what is given to us here, so instead of writing it in this way, you can rewrite your f of x function that would be maybe that's so this would be -x plus 3 plus take your remainder over x plus 1. So this is the rewriting that they're talking about. So you can rewrite it as quotient plus remainder over the divisor. However, for your asymptotes, oblique asymptote, you're only interested in the quotient. So since again, your polynomial was x squared, remember the quotient is 1 degree less than that. So you will be at -x plus just the quotient. So be careful when you're going through these examples and looking at the homework problems of what they're asking you for. Are they asking you to rewrite the function? Are they asking you just for the oblique asymptote? What's my vertical asymptote here, guys? Very good, yeah. Vertical asymptote, take the denominator, set it equal to 0, which we kind of already did that for the synthetic division. And that's going to be your vertical asymptote. So you will see how they're giving you x equals and y equals boxes. that's an indication that they want all the asymptotes for the function, not just the oblique or one of them. Okay, so our x equals is vertical, that will be -1. Our y equals is the oblique, which will be the -x plus 3. So let's go ahead, check this. And all right, questions on finding the oblique asymptote using synthetic division? All right, guys, so this table also might not be a bad thing to paraphrase it or copy it for the test. This kind of walks you through all the three different asymptotes. So again, vertical asymptote is take the denominator, set it equal to 0. For the horizontal asymptote, if the numerator has a smaller degree than the denominator, so that can be just a constant term on the numerator and x on the denominator, or you have x on the top, x squared on the bottom. If the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is at y equals 0, right? The x-axis. The degree is equal between the numerator and denominator, then it's going to be the ratio of your leading coefficients, right? So they were both x on the top and bottom, like we saw. And then, of course, if the numerator has a higher degree than the denominator, that's when you're going to run into oblique asymptotes, and that's where you use synthetic division to figure those guys out. Let me see if I have another example of this with the past. Find the limit, okay, this one's actually asking you to find horizontal asymptote. So recognizing the question might be important because remember when we had done, it just flew out of my head. I am so sorry. What was I gonna talk about? We did it on Tuesday. Leading coefficient test. Thank you. So leading coefficient test questions also kind of look like this, right? Because they had that limit with the x heading to positive infinity, negative infinity. But if you kind of get the concept, you can do either of those questions, okay? So that was for the leading coefficient test. This one is asking you to find the horizontal asymptote. So what you're looking at is, okay, the degree of my numerator is smaller than the degree of my denominator, right? I have a constant term 2 on the top, x cubed on the bottom. So this is again of that format where my function value is going to be closer to 0, because again, as my x gets really, really large, my fraction is going to head towards 0. So your y value is going to be getting closer to 0, which means your limit is heading to 0. So you're not typing in the equation here like we did in the previous examples. You're just putting in the final. So you're just going to say the limit is approaching 0. Okay, but this is a horizontal asymptote question. So graphing will be very similar to what we had done in the last section. You know, talk about symmetry, see what intercepts your function has. And that would be both for x and y intercepts. And then, of course, your asymptotes are going to be crucial because that's where we know what the behavior of our graph is going to be. So start by finding the asymptotes. If we were drawing this physically by hand, you do want to draw dashed lines because that tells us that those are imaginary lines, right? They're not actually there, but we at least know where those asymptotes would be. So symmetry, intercepts, and then of course, you know, as many points as you can to kind of get an idea of the shape, and then we can draw our curves. Now, of course, we're not graphing by hand, but kind of having those techniques definitely helps us. So you can see the first thing they're asking us to do is find the domain. You will also notice at the top of the question, they're telling us that this function is not in lowest terms. So this is actually what I was talking about before. Your graph will behave a little bit differently because it's not given to us in lowest terms. But let's start by finding the domain first. So domain, again, you take the denominator, set it equal to 0. So the only number we cannot include on our domain is going to be 3. So you can do anything between negative infinity and positive infinity. Just don't include 3. So that would look like negative infinity to 3, union 3 infinity. Which also, remember, is the same calculation for finding the vertical asymptote. So your vertical asymptote is going to be right there at x equals 3 also. And that's kind of why it's not also included in the domain, so they're interconnected. Okay, let's start by putting our domain in. So parentheses, negative infinity to positive 3, and then from the other side, positive 3 to positive infinity, and let's get our unions. All right, so this is kind of what I was talking about. You know what, let me save this because I think it's. Look at 3 of the graphs. They don't look like they have a vertical asymptote there, right? Because we're not seeing that behavior kind of like what you're seeing on graph B. But if you look at graph B, where is that vertical asymptote? That's that vertical dotted line. Is it at x equals 3? Where is it at? Actually, that's -3. They're doing it in 2s. But we know it's on the wrong side, right? We know it's not on the positive side, which is where +3 should be. So we know this is on the wrong side. So I think that's good enough to tell us he's not the graph. So your graph is actually going to look like one of these A, C, or D. So what's happening here is because this function was not given to us in lowest terms, we will actually need to do that. So we have x minus 3 on the bottom, but we can actually factor that numerator. You have x squared minus 9. What can we factor that into? Hey, Jessica, I'm not able to see you. I'm seeing the ceiling. Thank you. How do we factor x squared minus 9? Yeah, you have to use difference of squares. Very nice. So if you have x squared minus 9, that's the same thing as x squared minus 3 squared. So remember, that's your difference of squares format that factors into a plus b a minus b. And that's what we'll do here. It factors into x plus 3, x minus 3. And you can see when we factor it, one of these factors actually can cancel out, right? So we end up getting a simplified version of this, which is actually not even a rational function anymore, right? It's just the x plus 3, which is a linear function, a straight line with the slope of 1 and the y-intercept at +3. But that is why we did the domain first. So that way we knew 3 cannot be included in our function. So what happens here, guys, is when we graph this fellow, you actually have to leave an open circle for where 3 is not included in your graph. Because, you know, the original function was still a rational function, right? It's only when we simplified it that it became x plus 3, but you cannot ignore the fact that x minus 3 was my original denominator, which means I still cannot include 3 in my function. So that's actually what's happening here, is we have to look at the functions where you have the open circle at x equals 3. So same thing, right? This is on the negative side, the open circle, so he's gone. This one has no open circle at all, right? It's a full continuous line, so he's gone. That only leaves us with one option, and you can see. And again, they're doing this in 2, so this is a 2, this is a 4, so this is actually where your 3 will be, and that's where your singular is added. So that's a little bit of a difference that happens if the original function is not simplified, and then we do end up simplifying it, it does affect what the graph finally ends up looking like. Alrighty, so this will be our graph. That was option D. A question on this example here? Anybody on Zoom, did you guys have an question on this? So we understood, right, why we had to leave that little open circle on our graph? You guys? Yeah, okay. All right, what do we got next? You know what, let's do this example here. Again, go ahead and tell me what the domain for this guy will be. What numbers do we have to leave out from the domain? Very good, yeah. So this will be negative infinity to negative 3. Negative 3 to 3. 3 to infinity. Which also tells you your vertical asymptote is going to be at positive 3. Now this one cannot be reduced down, so it is already in lowest forms. What will be the horizontal asymptote for this guy? Seeing as how the degree of my numerator is less than the degree of the denominator. Daniel? No, if the degree is less, then remember you're actually at 0. So when the degree of the numerator is less than the degree of the denominator, you're going to be at the x-axis, y equals 0. So basically you have a horizontal asymptote here. We have a vertical asymptote here and another one here. So your graph is going to be kind of sandwiched between all of those. So let's take a look at what this guy will look like. X minus 1 and then x squared minus that. So take a look at, let's see if I can do this vertical minus x equals 3. X equals negative 3. So those are our vertical asymptotes. Of course, at the x-axis is the horizontal. So you can see that's exactly what's happening over here. As your graph on the right-hand side is getting closer to the x-axis, you can see it's getting close to the x, but your, so y value is getting closer to 0, but the x is headed to positive infinity. On the left-hand side of the graph, again, you will see as we're getting closer to the x-axis, your y value again is getting closer to 0 coming from the negative side, but your x is now headed to negative infinity. So that's with the horizontal asymptote. Now, this is the example where I was talking about where sometimes your graph will cross the the horizontal asymptote. So you will see in the center of the graph, we do actually have an x-intercept because that's where my graph is crossing the x-axis, but that can happen with an x-intercept, not with a, not x-intercept. With the horizontal asymptote, you can actually cross the horizontal asymptote, but you will not do that with vertical. On the vertical side, you can again see that your graph is getting closer to this line, right? Y equals negative 3, and you can see how those x values are getting closer and closer to negative 3, but your y value will start heading towards positive infinity. On the negative side, again, you're getting closer and closer to negative 3. You can see how that number is getting smaller and smaller for the x value, but your y value is actually going to get larger. Same behavior on this side. Your x is getting closer and closer to 3. And your y is starting to get larger. And then same thing on this side. So that's kind of what those vertical and horizontal asymptotes will end up doing. You can check that same calculation here. Your X is getting larger, but your Y is getting really small. Okay? But what if we saw something like this guy? This is gonna have an oblique asymptote. So our vertical asymptote here would be at X equals 1. So that would be this line here. What's the oblique asymptote here? And we know this is oblique because the degree in the numerator is larger than the degree in the denominator. What is your oblique asymptote going to be? We just talked about how to calculate it. Let's calculate it. What's our oblique asymptote going to be? So you're taking X minus 1, setting it equal to 0, which means we're actually dividing by 1. You've got 3x squared, and you've got negative 4, right? Which means you're missing the X term. So we put a 0 for that. Bring down the 3. 3 times 1 is 3. Add. 3 times 1 is 3 again. We need that negative number. That's your oblique asymptote. That's going to be positive 3. So let's 3x squared minus 4. So let's see, our oblique was y equals 3x plus 3. And our vertical was x equals 1. So let's get those lines in there. And you can see where the vertical asymptote is. That's the red line. The blue or purple, whatever that color is, the same thing's happening, right? It's getting closer and closer to that red line. So as your X value starts getting closer and closer to 0, your Y value is going, sorry, not 0, 1. Your Y value will start heading towards infinity. On the other side, the same thing is happening. Your X value will be getting closer and closer to 1, but your Y value will start going towards negative. With the oblique asymptote, you can kind of see, and I know it's not showing us like the good shape, but you can see where that oblique asymptote is coming in. So as you zoom in, you will see there is actually a gap between the graph and the oblique asymptote. So again, as you are going higher on the X side, your growth on the X axis is going to be much smaller than the Y, right? The Y is going to be growing a lot faster because again, you're heading towards that asymptote in that sense. But you will notice there is no horizontal asymptote here because that's what happens. You either have the oblique or the horizontal, not both. And then this last example over here is actually similar to the one we just did in MyMathLab, because you will see this is again actually not in the lowest form. So this will can be reduced to a lower form, and so its graph will be effective like we saw in that one example. So again, you guys can find the videos for these handout examples in the spring 2020 video lectures, if you want to go take a look at that. But the last part we want to talk about, guys, here is how to solve these rational inequalities. So again, you can do this by using a graph, or you can do this by using the test point method. So let's take a look at our example here. So they want us to do this using the test point method. So let's do it on that. All right. Let's look at this little guy here. So one thing you want to see is that little statement above the blue box that says a rational function can change sign only at a zero of the function or at a vertical asymptote. So if you are going to be at the x-intercept, then on the either side of x-intercept, you can see the changes in sign, or you can see the change in sign on either side of your vertical asymptote. So with horizontal and oblique, you're not going to see that. It's going to be at the zero of the polynomial or at the vertical asymptote. So the steps for using the test point method is basically saying same thing, bring zero on one side, put your inequality on the other side. The ratio of two polynomials in lowest term should be on one side. Find all the zeros for your polynomials, that's including the numerator and denominator. So you basically set each of your numerator denominator equal to zero. Find out what those numbers are. The rational function is undefined at zeros of the denominator. That's of course where we know the vertical asymptotes are. And then from locate the zeros from step 2 on the number line. And then using the test point, we'll see where we have positive and negative signs. So very similar to the test point methods we've done, but here you've got to include both numerator and denominator. So let's take a look at this guy. Our inequality is on one side. It's in lowest term, so we don't have to do anything with that. So we can actually start by finding our zeros. So we take the numerator, set it equal to 0. We take the denominator and set it equal to 0. So that will end up giving us x equals -2, x equals -5. So we put that on the number line. Let's see, -5 will come first, and then -2. What test points can we use for this one? So let's start on the leftmost interval. What would we use between -infinity and negative? Sure. Between -5 and -2? And then between -2 and negative. Right, we've got our test points. So let's check them. So we're starting out with x equals -6. So that will be -6 plus 2 on the top, -6 plus 5 on the bottom. Which is what, -4, -1. So +4. So that means this sign here is going to be positive. Let's say we did x equals -3. So that becomes -3 plus 2. And then what is that? -3 plus 5. What will this give us? Positive, negative? You can see that? Looks like it, doesn't it? Because we'll get -1 on the top, +2 on the bottom, so this will be a negative sign here. And then the last one, we did x equals 3. So that's what, +3 plus 2, +3 plus 5, and what will this be? Positive, negative? Yeah, so that will give us 5/8. Now, your inequality is greater than equal to 0. And I really want you to think about this carefully. The -5 came from the denominator. So remember, this is where our vertical asymptote is. The -2 is going to be your x-intercept. Because how you write your interval notation is going to matter. So since we are talking about inequality being greater than equal to 0, we're interested in basically where the y values are greater than equal to 0. So what do you think our interval notation, our solution set for this guy will look? where your y value is greater than and equal to 0. Let's start with the greater than. What interval are we seeing the greater than? So that interval would be no, -6 was the test. -5, yeah. Where other place are we seeing y greater than 0? What other interval? -2 and going where? Very good. Yeah, so these are both places where we have the plus sign, right? So we know the y value is greater than 0. So now the question is, where is y equal to 0? Because that is also part of our inequality. So where is y equal to 0? Is y equal to 0 at -5, -2, both, 1, either or? Y equal to 0 at which point? Yes, very good, because that's where your x-intercept is, so that is where y is equal to 0, which means you are including -2, but you are not including -5, because remember, again, that's where the vertical asymptote is. That means we cannot include him because he makes our denominators. So this is going to be our solution set, -∞ to -5, not including that number. Then union, including -2 to positive. So let's put this in, -∞ to -5 parentheses. And then bracket, -2 to positive infinity, and then we'll do other. Check that, see what this has to say. That's the one thing, like I said, you have to be very careful about is where is the vertical asymptote and where is the actual x-intercept. So remember, the numerator polynomial gives you your x-intercepts. The denominator polynomial gives you the vertical asymptote. Okay. Jessica, Danny, Daniela, question on this example, guys? Yeah, okay. How about you guys here? Okay, so that was the one example I had, but do you want to see another example? Are we doing okay? How are we feeling about this? Want to see another example? Not in the lowest terms, that might be a good example to work with. They're saying about using graph, but we'll use so x minus 2 on the top, x squared minus 4 on the bottom. This is again not in lowest terms, guys. So let's first start out by figuring out where the domain is not working, and then we'll break it down and make it. So what's our domain? Okay. Very good. So again, with the two numbers that we are discarding are both positive and -2, because that's what this guy factors out into, x plus 2, x minus 2 on the denominator. So that's where the two numbers are coming from. Now, technically, we would have said even the vertical asymptote should be at these two numbers, but that will not be the case because my function is not in lowest terms. So let's put this guy in lowest terms. You've got x minus 2 on the top. The denominator factors into x plus 2, x minus 2. So like we had seen in that one example, these guys will again cancel each other out and you'll just be left with a one on the top. So we'll have one over x plus two. So that means technically, this is your vertical asymptote, right? At x equals -2. This is probably where your function is going to be undefined, but I doubt it's actually going to be a vertical asymptote. So if you were using the test point method, obviously if we set this equal to 0, it's not going to work because there's no x there. So we just set this guy equal to 0, which will give us -2. So your intervals you are looking for would then be finding a test point here and finding a test point here. So what number can we use on the left hand side? Sure, it works. So -3 here, and on the right hand side? Sure. Alrighty, so let's check these guys. If we did 1 over -3 plus 2, what will that give us? Over -1, which comes out to be -1, so this guy will be negative here. With 1 over -1 plus 2, what will that give us? One over 1, so that comes out to be a 1, which will be a positive number. And you can kind of see that same thing happening, what your textbook was talking about. On either side of the vertical asymptote, you can see a change in sign, right? So we've got negative on the left, positive on the right. All right, so which interval is going to satisfy the inequality where they're basically wanting to know where is your y value greater than 0? And how will that x equals +2 where our value is still undefined end up looking like? So while you're thinking about that, let's go and see what the graph of this guy looks like. X minus 2, x squared minus 4. Happen. So what are we seeing here in this graph? Where's your vertical asymptote on the graph? Yeah, so we're definitely seeing the x equals -2 as our vertical asymptote. What is something we are not seeing that we should have seen on this graph? Because in the original function, we said +2 also could not be included, right, in the domain. So, and that's kind of something, you know, again, we're kind of restricted by technology. If we would have drawn this by hand, we would have put in limits. Okay. Now we know from our calculation here with the test point method that since we are looking for where the y value is greater than 0, we know that's this interval, right, where we got the +1 as our, positive answer for our test point of -1. So that's this interval right here between -2 and infinity, which we can see that's this part of our graph, right? Because that's the one where all my y values are positive. So how would you write that solution set? Is it just -2 to infinity? Or do we need to modify it? The answer is right in front of you. I just want to see if you're able to identify it and write it down. what is our solution set? With this inequality? We know it's this interval. But we also know we cannot have x equals 2 because that makes my original function undefined. How are you going to write your interval notation for the solutions? Anybody on Zoom want to share an answer with me? Now, some of you have already done this homework, so I imagine you guys have run across this example already, no? Okay, expand out that line. Okay, Danny, you're saying -2 to infinity. All right, let's check that. How about if we take this number line and expand it out? So of course, -2 and 2 are the two numbers we said we cannot use. We know there's a vertical asymptote here, but we also know there's an open circle at 2, right? Because that's where it's undefined. So if we are using this interval from -2 to infinity, well, I can use everything in between -2 and 2. But I cannot use 2 because that's where my open circle is. So that means I can only go from one side of the 2 to the other and use that. So the way you write your notation would be not including -2, going to +2, obviously not including that. And then you pick right back up from the other side, union 2 to infinity. So these functions that are not given to you in lowest terms, they will always give you that one extra number where you're gonna have, something undefined, right? Because this one was where my original function was undefined, but when I simplified it, it disappears because once I simplify it, it's gone. So you have to remember, but my original function was still not using that number. So when I simplify it, that number still cannot be used. Okay, so those are some of the things you will have to be very careful about when you run into these not in the lowest form rational functions. All right, guys, so do we see why it's not just -2 to infinity and why that 2 needs to be used? Yeah. On Zoom, are you guys okay seeing why the +2 also had to be left out? Yeah, Danny, are you okay with that? Yeah. Okay. Anybody else have question on this, guys? Okay, and I think that was our last example. There's an application problem in here. You're not gonna see that in homework, but again, if you just wanted to see that as a reference, this guy is here. And then I think that was the last example, yeah, because we jumped to the chapter 4. Alrighty, so again, guys, you are working for chapter 3, 3.1, all the way to 3.5. Please make sure you have 90% on each section. Those of you who need to make up for your attendance, that leaves you, I guess, this evening, tomorrow, Monday, and I guess half of Tuesday. So if you need to make up attendance, please do that before class. If you don't have 90% attendance, you don't get to take the exam either. So please make sure. And if you are unsure of your attendance, just shoot me a quick email, or if you want to say that after class, I can answer that question for you also. And then remember, guys, Tuesday is exam day. You will need to be in class physically taking the exam, or you can take the exam with the testing center, but not with, on Zoom. You need to be here physically. So everybody who's taking an exam on Tuesday, make sure you are in class.